wondered what gives bile its characteristic color? It's all down to the yellowish-brown compounds known as bile pigments, bilirubin and biliverdin to be precise. These are byproducts of the breakdown of heme, a component found in red blood cells. Bilirubin, the main bile pigment, is born when heme is broken down in the liver. It then makes its way into bile, aiding in the digestion and absorption of fats in the small intestine. Biliverdin, on the other hand, is a green pigment that transforms into bilirubin in the liver before being excreted in bile. These pigments give bile its unique color palette and are eventually expelled from the body through feces. But they're not just there for decoration. Changes in the levels of these pigments can signal potential liver or bile duct disorders, among them jaundice, which is characterized by a yellowing of the skin and eyes due to an excess of bilirubin. So we see that the colors of bile are not just for show, but serve important functions and can even hint at our health condition. Now, how would you know if there's bile where it shouldn't be, like in urine? Enter the foam test. This simple check involves collecting a urine sample in a clean container. Gently shake the container to mix the urine and then observe the surface. If you see foam that lingers for more than a few seconds, this could indicate the presence of bile. But what does that mean? Normally, bile is produced by the liver and stored in the gallbladder, and it shouldn't show up in urine. If it does, this could signal potential issues with the liver or gallbladder. However, it's important to remember that the foam test is not a definitive diagnostic tool. If you suspect bile in urine, it's crucial to seek further testing and evaluation by a healthcare professional. The foam test, a quick and easy way to detect potential issues, but remember, it's just the first step and not a diagnosis. But what if we need a more precise measurement of bile pigments in the body? The dye dilution test comes into play. This method measures the concentration of bile pigments, such as bilirubin, in the blood. It uses specific dyes like bromsulphthalene or indocyanine green, which are absorbed by the liver and excreted into the bile. Here's how it unfolds. A known quantity of dye is injected into a vein, and its concentration in the blood is tracked over time. As the dye is processed by the liver and excreted into the bile, its concentration in the blood decreases. By observing this rate of decrease, we can assess the liver's efficiency in handling the dye. Moreover, the concentration of the dye in the bile is also measured, either directly from the duodenum or indirectly based on the blood concentration. This data allows us to estimate the liver's capacity to excrete bile pigments. Though not common in clinical practice, the dye dilution test provides valuable information about our liver's function and health. From a simple foam test to a complex dye dilution test, we've seen how we can detect and measure bile pigments. But what about the diazotization test? This chemical test helps us detect the presence of certain functional groups in organic compounds, specifically primary aromatic amines. Intriguing, isn't it? The process involves the reaction of the amine group with nitrous acid, forming a diazonium salt. This salt can then further react to create a colored compound. The color change can be observed, giving us a visual cue about the presence of these functional groups in the compound under investigation. While it may sound complex, this test is a crucial part of organic chemistry, helping us understand the structures of compounds and their functions. Just like the foam test and the dye dilution test, diazotization plays a significant role in our quest to understand and monitor our body's chemistry and health. The diazotization test, another tool in our arsenal to understand and monitor our body's chemistry and health.